welcome to my presentation. My name is Pouria Bigvand. I'm since around 10 years with AUCOTEC, and today's presentation is about non-stop cooperative plant engineering from feed to operation. So I'm going to explain a little bit about the challenges that are existing in the plant design, more or less about the workflows for plant engineering of production plants, and a little bit about the solutions and possibilities that we have in the market for these challenges. So first, who is AUCOTEC? We established 1985, around more than 30 years ago in Hanover, Germany. We have around 220 employees around the world in 9 subsidiaries and 27 partner countries. We have around 45,000 installed licenses and in-use licenses around the world for our software. And we have about 30 million euro turnover per year. And of course, we had around 100% or doubled the revenue of the company in last 10 years. So very healthy company and very bright future for our products based on the customer base and the prospects that we have. So first, let me explain a little bit about the challenge that I want to address. What is the problem actually? This picture that you see on the left side is actually the numbers of the greenfield plants, the main and big ones around the world, for last 3 years and next 5 to 10 years. The main challenge for all the greenfield and also the brownfield projects is basically the increasingly complex requirements for engineering of the production plants. I just try to list some of these challenges on this slide, and you see that the first one is the agile parallel engineering. Nobody is able or wants to do the sequential engineering anymore. So everybody wants to focus on the agile engineering and of course a parallel engineering. What does that mean? It means that nobody wants to wait until the P&IDs are completely finished so they can start to do the instrumentation. They want to start as soon as some part of the P&ID is finished. They want to start to do the instrumentation in parallel. And of course, when there is a change, that change should be applied in all the disciplines in an agile manner. So second approach or the second challenge is that the international cooperation of multiple contractors. This means that no project is done locally in one single country, no main and big project. There is almost always, there is a cooperation between many different companies and of course international companies from different teams around the world, from China, India, Europe, US, and they all work together for building a project. And of course, these different people around the world, they have different languages, they have different cultures, they have different workflows, standards and unit of measurements, for example. So they are coming from different educations, different aspects of the design of the plant. And they have to work together in one single project all together. Beside all these different things or different aspects of the plant, there is also an aspect of change management. If somebody changes something from India, for example, or China, what are the consequences of this change? How should it be recognized in US or in Europe, and vice versa? And the change management is one of the major factors for designing a plant which is a global plant. It's global engineered. And of course, we have various and inconsistent sources of data. Every one of these contractors, they have different tools, they have different workflows, and they put the data in the single source or in the central plant from different sources. And that's why it makes it very complicated to manage all these different sources and inconsistent sources to come up with a final single database or data model for the plant. And of course, future technologies, for example, modularization, augmented reality, all predictive maintenance, all these additional possibilities that are existing for the plant design, they are needed to be done with the data model. They need some data to work. And therefore, all these things that are needed for the future and for the increase of the efficiency of the plant design, they are also a challenging point or a complex requirement from the designers and plant engineers. So these are the challenges that I wanted to address. Now, what can be the solution? Conceptually, what is needed is basically a single and central cooperative platform. So you need a cooperative platform that all the disciplines work together on that platform and they collaborate together. Of course, we need a central, which we call the single source of truth, data model. So you cannot have parallel data models against each other. You should have one central data model that everybody is working against that data model, and they just try to mature that data model day after day from different sources. And of course, we need an intelligent delta management and change management, because once you have the data model, then the changes and the consequences of those changes are extremely important. If somebody changes the flow rate of a pump, then that flow rate have consequences on the pipeline, on the consequent valves, and so on. So the consequences of the changes is extremely important to be tracked and to be identified by all the engineers involved in that project around the world, of course. So what we provide as an AUCOTEC is engineering base. Engineering base contains a versatile data model for all the disciplines. For all the disciplines, I mean from the feed up to the operation. It contains one database, one set of standards, and one working platform for everybody. This means that this platform, as an engineering platform, can be used by everyone around the world from different environments to design that central plant or project. It provides a link between digital twin and the complementary systems. Of course, there is nowhere around the world that you say that I have just one system. There are a lot of systems around it for calculations, for simulation, for 3D design, mechanical design, and they all should be synchronized to a single source of truth. And that is what engineering base is also providing. For a change management, it offers the possibility of changing all the changes, seeing all the changes in the plant, and of course see who, when, what, and why they change something. So this is really important to track all these changes up to the level of every asset and every individual component, and also see why something has changed. So people can write a comment about a change that they make, and you can track the reasons behind the changes. And of course, engineering base is supporting you to see the consequences of the changes when something is changed in the plant. And of course, it has the direct data relationship with all aspects of the plant. So I will explain a little bit about this point in next slide. So plant has different aspects. It starts with the proposal, feed, process, instrumentation control, electrical, automation, and maintenance. You see that in this picture, this is the map of engineering base. Engineering base is in the core, and all the disciplines around it can work with engineering base to design a plant. Of course, there is no boundary between them. There is no boundary between feed and process or process and instrumentation. There is no data import and export. They are all integrated together. And of course, there is no arrow. This means that it's not necessary that you finish one step and then next step can start. As soon as you have some baby steps in the process, for example, some modules on the PNID, then instrumentation and control can start to work on them and then do the job in parallel to the PNID until the PNID is finished. So it's a parallel engineering. And of course, there are a lot of things around these points. For example, integrations, cause and effect, change management, tendering management, project execution with subcontractors. These are all the points that are relevant for all the engineers. If you're in an automation, you can have subcontractors. If you're a process guy, you can have subcontractors for certain black box modules or MTPs. And that's why we have this next layer of the integrations and possibilities to the core engineering of the plant. So how does it work in reality? How does it work in the data model of engineering base? Let's take this a small example. It's a very small plant, but it's a very complete one. So you have the tank, you have the pump, you have the valve, you have the wires, cables, terminals, and the DCS at the end. So it covers a complete life cycle of a plant, more or less, for the design phase, but in a very small scale. And now the next step, or the first data model that you need for this plant to have the complete digital twin, is the equipment model. So equipment model, for example, we have a tank, then under the tank you have a nozzle, you have a sensor, you have a valve, and then below that you have a pump, you have a motor. So this is the complete equipment or a physical perspective of the plant. You have the data model of the plant, and this data model represents the physical aspect of it. Then next step is the system or the functionality of the plant. First of all, I have a plant that produces something that's the functionality of the plant. Below that, I have a subsection of the plant for certain functionalities, and then below that another subsection, and then at the end I have, for example, a mechanical tag for my tank, and then below that I have a measurement tag, I have actuator tag, I have PCE loop. So these are all the functionalities of the plant. And of course, there is an association between the mechanical tags or functionalities and the physical devices or equipment. So you can see that, for example, for my mechanical tag tank, I need a physical tank and I need a pump. Or for my actuator tank, I need a valve and I need a wire. So there is an association between the functional and physical world. Next step is the civil engineering. All these equipment are located somewhere in a building, as a location, as a physical location, or they are located in some logical area, for example, a Wi-Fi zone or fire zone or security zone. And of course, again, there is an association between the civil engineering buildings and every physical device. So easily you can find out, if you go to a room, what are the equipment that are included in that room. Or if you go to an equipment, you can find out where is the location of this equipment. So you see that these aspects are all associated together. And the last aspect that you need to complete the digital twin of the plant is the dynamics of the plant. So dynamics of the plant means that a plant can have different scenarios for production. You can produce different products. We call them scenarios. And each of these scenarios can have different operation modes. For example, a startup, shutdown, operation, normal operation, end of run, or emergency shutdown. And of course, again, there is an association between the individual operation modes and equipment or functionalities. For example, you can say that for a certain operation mode, I need a functionality, for example, firing system, and for certain functionality or operation mode, I need certain devices that should be in a certain state. For example, a valve should be open or closed. And all these models together at the end will end up in a digital twin. And you can recognize here that the documentation of the plant is just a side product. This means that when you have the complete documentation, they are nothing but just showing what is inside the data model. It means that when I have a pump, I can represent this pump on different diagrams. For example, on the PNID, on the 3D design, on the reports, on the instrumentation and electrical, or on the cabinet. It doesn't really matter. I have an object, and this object have a representation on the diagrams. So it is impossible to have inconsistent documents, because once you change something on the PNID, you are not actually changing a PNID. You are changing an object, and this change will reflect itself automatically on all the other diagrams that have a representation of that object. So inconsistency between the diagrams is actually impossible. And of course, there is no question about what type of diagrams can be covered with engineering base. Of course, all the diagrams that are 2D diagrams can be covered because they are just representing the data model of the plant. So now let's see what is inside engineering base when we go directly into engineering base. So you see that this is the engineering base, this is the user interface. It is really important for us that the user interface should be very user-friendly. And you see that if I open a database, I have different projects here, and I have a lot of other folders, which I don't go through them right now. But the concept is very similar to the Windows. That's what we are following, the Microsoft concept, which is very user-friendly. So easily you can create a new folder, and then you can easily name this folder, of course, and then drag and drop different projects or different items in that folder. You can easily open multiple projects, copy-paste from each other. For example, if you have a PNID from one project, you can just copy it to another project and then start to work with that. And of course, that contains all the data model. It's not just about the diagram. You see that we have the 4 main folders: equipment, system, area, and location processes. And on every folder, we have different data model inside. So for example, if I go to the equipment folder, you see that I have the heat exchanger, I have the, for example, unit operations. These are my unit operations, and so on and so on. So if I go to the documents folder, then you see that I have the complete documentation here. Of course, you can create as many folders with every name that you want here, with every standard that you want to follow. But here it contains all the documentation of the plant in one central place. So you can create, of course, new folders. But if I go to the some of these folders, for example, if I go to the feed part, then you see that on the PFD, you can preview the PFD here. Then the next one would be, for example, the block diagram. You can see the block diagram here. On the process side, we have PNIDs, for example. This is the PNID. Then process automation. This is the single SCD diagrams. Then, for example, the loop diagrams here. For the instrumentation, we have the electrical diagrams, for example, for PLC cabinets. We have the circuit diagrams, we have the cabinets here, we have the connection diagrams that show the connections between different cabinets here, for example, and so on and so on. So you see that, for example, also HMI, the automation for the logic diagrams. And what I want to say is that basically all the documentation of the plant are existing here, and all are reflecting the data model, central data model of the plant. So it's very, as I said, it's very important that the user interface is very simple to be used and very convenient for the engineers. So for example, if you open a PNID and you want to modify something on the PNID, you see that the environment changes to the environment that a PNID designer is comfortable with that. So on the right side, you have the tool palette, we have the modules that are verified by some administrator. And on the left side, you have the data model. And on the bottom, you have the rule-based and the errors that you have on your PNID. Basically, all the rules that are checked every time, and then they can be verified by the system to be valid. Every PNID designer, every process, just we can drag and drop a module on the diagram, and by that, actually, you're adding the complete data model behind the scene. Complete data model means that everything you have to define already for this module. If you define already the wiring and the terminals and everything else behind this module, it will be used and it will be added to the data model. Of course, the rules are checked at the moment to be seen and verified. Everything that should be applied, it will be applied behind the scene. And all the engineers should do is to decide which module should be added where and how it should be added to the system. So if there is an error, you can see that there is an error. The system will guide you to fix that error live based on the rules that it has, based on the knowledge base that it has, and then it can support the engineers. So this is just an example of how engineers can work effectively on a platform which is applicable for all the engineers around the world. So it's not just a conceptual cloud platform or something. It is really a software that can be used effectively by engineers around the world, like a PNID designer, but behind the scene is actually a very big platform that contains the data and the complete plant data model from all different sources around the world. Here you see the reports, which are updated automatically without any effort, zero time to update the reports, because they're just looking to the data model of the plant and they just represent what you have in the data model. So time for creation of the reports, absolutely zero. And that's how engineering base is basically designed. Now, where this platform can be used? Of course, in everywhere that you design a production plant. These are some examples that you see, our customers that are using engineering base in these examples. But everywhere that there is a production plant and you want to design a plant, engineering base is the platform to be used for single source of truth to design the complete digital twin of the plant. What engineering base offers? This picture that you see on the left side is actually a representation of engineering base. You have a plant, and then as a shadow of the plant, you have the complete documentation and data model of the plant. That's what you see on the picture, and that's what exactly represents engineering base. A unique engineering platform for complete plant lifecycle with its object-oriented, versatile data model. This means that you have a versatile data model for different disciplines, for instrumentation, process, and automation, and everything else. It is object-oriented, so every object is there to have the attributes, to have the associations, and to have representations on different diagrams, and it is covering the complete life cycle of the plants. Of course, it has a very flexible and modern architecture. The platform is very modern design, because if you have this globalization of the projects around the world, you need these different levels. We have one level for client, as I showed it a few seconds ago, that you can design something. Then we have one level for the business logic that analyzes the data. And then we have one level as a database that is storing all the data. And these three levels ensures a full and very high efficient performance to design for the designers to design the plant, independent of the platform behind it. As I said, the platform is in a central database, but around the world, engineers can just log into the system, and then they can start to design like it is a local system to design something. And that's very convenient for the engineers, because they will not be bothered with this complexity behind the scene for a very big platform for cooperative plant engineering. Of course, we tried a lot to keep the look and feel based on Microsoft, very user-friendly and very consistent to the disciplines. Means that for the thing which is user-friendly for a process designer is different from what is user-friendly for an automation designer. And that's what we considered, to have different environments for different disciplines, so they can very efficiently work and build up the plant as fast as possible. And of course, a lot of other possibilities like cloud compatible, software as a service, and these kind of things are possible with engineering base. But one of them, which is very important, is data as a service. Data as a service is a possibility that you can send or receive the data using web services, and that means that every third party which doesn't have engineering base can receive and send data to engineering base. If you have a contractor that doesn't need to access to engineering base with full capacity, but he just needs to view some data and get some data for some, for example, maintenance tasks, then they can use data as a service, and then they can access the data from their own systems. And of course, an open API will provide the possibility of doing a lot of automation possibilities inside engineering base. So one of these accessing of the data example is actually viewing the data. And this is very important for example, the operators of the plant or for the maintenance colleagues. They want to view the data, but if you give them an engineering tool, that's too much for them. They want to have something which is very convenient and easy and maybe touch compatible, and they can take a tablet to the plant and then they can view the documentation. Of course, navigate through the pipes, navigate through the cables and wires, and that is what we are offering. Mobileview is a solution that uses data as service and also exports from engineering base. And in principle, it provides the possibility of viewing the data from outside of engineering-based environment with a very simple touch-based environment user interface. That provides finding and viewing all the objects in the plant, for example, in the digital twin of the plant. Very easy handling, of course. And of course, for mobile applications, with tablet, with your mobile phone, with your laptop, whatever that is mobile is a browser-based solution, so you can just go to the plant and then view the full documentation of the plant. So it means that if you want to change a valve, you don't need to look for other documents that contain the instrumentation or the wiring. Everything is just there, and you can navigate for the process part, instrumentation, or electrical part of the plant. So as a summary, what engineering base is offering and what is engineering base? It's a single source of truth for complete plant data model. That is the core of engineering base. It relies on the model-based, data-centric, and future-oriented manner, and it provides the backbone for the digital twin. It increases the efficiency of cooperation. Once you have this single source of truth, we have the change management, you have the receive of these data sources from different languages, different systems of units, and so on and so on. You have a very high efficiency of cooperation of different contractors and different engineering teams all together. It offers a very high reliability on the data quality, of course, because everything is on the data and the documents are just following the data, so there is no inconsistency between the documents. It works with one versatile database for all disciplines. You don't have multiple databases that you have to synchronize. You have to synchronize the customizations and those things. It's a single database. It's a single customization. And it supports the entire plant lifecycle. This means that you start with the concept design to the process, instrumentation, electrical, automation, commissioning, and operation of the plant. And of course, it's based on decades of experience and feedback from our customers. So we have customers with more than 15 years, 20 years of using engineering base, and this engineering base is not built overnight. It's more than 600 man-years of development, and it is basically based on the feedback and the consultations that we got from our customers, and this 45,000 licenses that are used around the world, including our legacy products and of course engineering base that provides a platform for plant design and design of a digital twin. Thank you very much for your time. Thank you very much for your attention, and I hope you will have a good exhibition and day forward. Thank you.